I will talk about the project we did about 6 years. And it started originally as a kind of spin-off from fusion work. And you can see, I think, how nicely sometimes you can bridge over between different disciplines. We developed some kind of tools originally for fusion, and we very successfully were able to bridge this into this field of research. You see it's a small group, 5 people working on this in 6 years, which is for a theory group quite large, but for experimental it's quite small. The motivation behind this work is relatively easy. If you try to develop this raster for industry, each individual prototype costs about 1 million euro. Now, if you want to get into the market, they need approximately 20 prototypes, that's about 20 million euros. And if so guided by modeling research, you can reduce this number of prototypes by a factor of 2, you gain a lot of money. And our costs are extremely small, theory costs practically nothing compared to these kind of prototypes. Therefore, we are highly attractive for industry, helping them to develop the system. Our industry partner is mentioned here, it's Thales. I'll show you later some details of the system we have prepared. Some background, space propulsion, you all know this wonderful rocket stars in the 60s and 70s. Space propulsion originally was mostly driven by chemical propulsion. And the background of space propulsion is very easy. You apply a certain acceleration, mostly here through chemical propulsion. You have a total propellant mass, and if you just apply the second law of Newton, and you derive the relationship between the change of your mass and your acceleration, your thrust, you see that the total mass you need for a certain acceleration scales this 1 over the velocity. Now, in chemical propulsion, the typical exhaust velocity you are able to approach is 3000 meters per second. And this poses automatically a certain limit and the kind of need for certain masses you have to supply for starting such a system or in space just to making it transfer in orbit or to rotate this satellite or whatever you want to do. And that means here in the case of chemical propulsion, you see here a typical case that you have a typically payload ratio only of 6%. It's terribly bad. And now the question is how you can improve this. And obviously the key element to improve the situation is to increase the exhaust velocity. Now how to do increase? We are all plasma physicists and we all know what a plasma is. Therefore very early the idea of electric propulsion came up. And the idea is very simple. You combine a small RF discharge, you ionize the propellant, and you in addition add some grids to accelerate the propellant ions. Very simple, you see here a sketch and the running grid thruster on the bottom. And you easily achieve with such a system velocities up to 20 kilometers per second. And this means you gain a lot compared with the 3000 meters per second which you had in chemical propulsion. And this is the reason why people get so attracted by this kind of electric propulsion scheme. Now, you have seen here a picture of a grid thruster. That was exactly a first system which was introduced similar to the sketch I showed you. And you see here the attractivity of electric propulsion. Your payload rises dramatically due to this increase of your velocity, and that's very beneficial. However, if you then look at the pros and cons of such system, here you have a nice separation of ionization and acceleration, which allows you an independent optimization of the system. You have a very high efficiency. You can ideally shape your beam to minimize the interaction with the satellite. That's wonderful. However, on the con side, you have space charges, which reduces clearly your arrival current in the thruster. You have, unfortunately, especially limited lifetimes of your grids because you have very strong sputtering at these grids going on. And you have also a rather complex construction and the costly system architecture which the people integrating satellite systems don't have. Especially this grid sputtering is a very difficult problem, so to say, to overcome, because usually these gridded thrusters are limited to several thousand hours, and you want to go up to about 30,000 hours when you want to operate such systems. That was the reason that more and more people looked into grid-free concepts, and I will show you that in a minute some examples for one system. Now getting back to physics, I demonstrate you here a little bit the complexity of the system. Let's start with the plasma part. So typically plasmas you have in such a thruster channel dimension here, 10 to 18 per cubic meter several EV, and you get rather small device scales of say 10 to 20 microns. Now on the other hand, you want to understand also how this plasma which is created streams out and interacts with the satellite, the so-called plume part, the outer part of the system. Here, if you characterize there the parameters, you see that you end up now with device scales which are of millimeter scale. It means you have a bridging from micrometer scales to millimeter scales, and this you have to handle somehow also technically to be able to model the complete system, because mostly up to now people were concentrating mostly on the simulation just of the thruster channel, and that's a rather incomplete picture of such a system, because the interaction with the plume is as important as your thruster itself. Just to mention another landscape here, you have also your interaction of your particles with your surfaces, and this is very fast. Clearly, you have typically your picosecond scales. That means this you can well separate and treat this as an independent level, quasi-stationary. Now, what are the typical topics we address? Just to give you an overview, I listed here the 4 major topics from my point of view. We have typically the first part, that in the channel itself, in the system, we typically have non-Maxwellian distributions of the things. That means we have, due to the magnetic confinement we are using, you see later how these things are constructed, strongly kinetic effects, hero forces, all kind of additional effects. The mean-free passes of the system are such that you have no chance of equilibrating, and that means you need a kinetic model. Then the second problem is, you have plasma wall interaction, clearly destroying eventually your whole thruster system inside, but also eventually affecting solar panels, which you need for getting the electric supply for the system. Then you have, unfortunately, a rather complex expansion dynamics also outside the plasma system. That's a non-magnetized region, the plume, and there you have important interactions due to charge exchange collisions with your background gas, producing load-like structures, side flows to especially the satellite structures. And finally, we have eventually plasma and electromagnetic wave interaction, because we have a plasma sitting there which might suppress the communication with the satellite. Fortunately, this last topic is not a matter of worry. It was just historically a topic, but this was never really realized. Now, what are our tools? How can we help now the experiment to have a kind of predictive way, understanding the basic physics mechanisms and minimizing the number of prototypes and understanding the basic physics? We need, like I said already, a kinetic plasma model. Therefore, we took existing particle and cell codes originally developed for fusion and applied them in several complexity to model the system. It's important that you choose the right level of complexity. You don't want to use always the 3-dimensional full code, which of course has also the capabilities of consistently modeling the turbulence, but you want to use the 3D code also just for, so to say, calibrating your transport coefficients for a 2D version, just to be fast and productive, so to say, that you reduce your runtime. Then we have the combination which is necessary due to the interactions with the surfaces. Here, binary collision models or Monte Carlo models coupled to collision and cascade models are the typical choice. And then you might have to introduce also your neutral species. This you naturally do in combination with these kinetic models, also with a direct simulation Monte Carlo method, including the complete system in a consistent way. And in addition, just to reduce the effort, we apply also something we learned from fusion, namely a similarity scaling law, to reduce again the effort for calculating this real system. Now, like I said, at the end you have a self-consistent coupling of these methods. You reduce the empirical parameters by cross-calibrating the different elements from the higher level and combine these in such a way to have an optimized model. And usually you try to reduce this in a hierarchical order. Now, what is the system we studied? This is the so-called HEMP thruster, high efficiency multi-stage plasma thruster from the company Carlos. Here you see a sketch of the system and a photo of a mock-up prepared, ready, so to say, say, to be installed on a satellite. You see, the basic idea is relatively simple. Originally, Thales was producing drift tubes, and in one of the experiments 20 years ago, they unfortunately burned a hole into their tube, and they realized, oh, if it's burning a hole, we might be able to produce thrust out of this. And then they modified this kind of drift tube idea to this kind of thruster construction. Now, what is the idea? You have your anode, and then you have, in this case, 3 magnets ordered in this way, cylindrically really around this whole tube. In addition, you have a dielectrical ball following, so to say, this channel. And this structure of the magnetic field has now the following advantage. You minimize the number of positions where a plasma created within this system has wall contact. It's only guided to the wall by these so-called cusps when the magnets are in contact with each other. And then you have a large part of the system where you have strongly axial parallel fields, which makes, so to say, a relatively good connection between the system. You also see that in the center of the system, you have a direct connection from the exit to the anode. In addition, you need an electron source outside, mostly for keeping the whole system neutral. You don't want that if you have ions going out, that the satellite is charging up. That means you need a neutralizer on the outside. This you see here as the electron source, and this acts then also as a virtual cathode. For running the system, you don't need this, because you always have some free charges that just runs, but running on the satellite, you need it just for neutralizing. Now some details for the code, people, very shortly. Like I said, it's a standard 2-dimensional, 3-dimensional full thick code with Monte Carlo collisions. All collisions which are necessary for these xenon plasmas are existing. Clearly you need a secondary electron emission model, which is also implemented, and including that also the neutral dynamics, and we have also, like I said before, calibrated from 3D runs, an anomalous transport model, just to include also the turbulence. The trick I was mentioning before, you see on the right side, you can derive analytical scaling laws, which allows to keep an exact similarity of your solutions. And with this trick, we are able to reduce, so to say, the grid size we are needing to resolve without changing our debye length. And what is important, clearly, the ratio of the real-free passes and the Hall parameters and so on, all these are protected. That's a kind of clever trick, minimizing the numerical effort. Now, first results. You have seen the system before. This is now a potential solution. And you could have guessed immediately, just looking at the sketch before, that the solution will look like this. In the first contacts 5 or 6 years ago with the experimental group in the company, they were quite surprised, because what they expected was that they have a potential which is extreme step-like. And we from the beginning said there is no reason why there shouldn't be very pronounced steps, because due to this shortcut in the center, you have a very strong parallel heat conduction, which drives your system into a kind of equilibrated state and smoothes the profile. Exactly this you see, you have practically constant potential from the anode to the exit, and a very small step where you have the kind of cusp you have seen before. And then you have your exit, and this is perfect because this looks exactly more or less like the potential of a grid system. You have constant potential, then you have your drop where you accelerate your ions. It means we are able to design with this trick a grid-free thruster which looks like a grid thruster. That's a very nice feature of the system. Now, to give you some ideas, I show you now some average solutions on the domain for such a system. First, for the electron density, you see here is the system, that's the end, that's the exit, here's the exhaust that I visualized just for you the movement of some test particles in such a system. You see very nicely, starting from the source here at the outer part, the electrons are getting into the system because they walk up the hill. They are confined by your potential structures, they are accelerated, and then the first cusp is here. You see relatively complex measurement. Here's the second cusp with some additional, so to say, separation of the system, and then you see here the filling up. Especially in these parts at the cusps, there's strongly kinetic movement, and you can understand that you need a fully kinetic description for such a system. Any fluid model will fail miserably. We have no chance describing here the physics with this kind of approximation. Now look at the ions, really they follow mostly the same distribution as electrons because we have quasi-neutrality. I reduced here the time step just to visualize also their movement. Really they have a different characteristics. They slowly drift in the system between anode and cathode, and then at the end, where you have this drop, they just follow the potential drop, they are accelerated and produce the thrust which you want to have for your system. That means fine-tuning of this potential structure at the exit is the given kind of measure to optimize the system thrust and also clearly to optimize the distribution of the ions. You see already here, this is not so nice because you see some divergent structures. For interaction with the satellite, it's not so perfect. You can do better than this. There are better models existing which look different, but I'm not allowed to show them. This is now the neutral dynamics. It's again slowed down. Neutrals are much, much slower moving, and you see that's rather like you would expect. I mean, they are just flat in, then they are ionized a little bit, have a rather streaming out characteristic, but you also see that in this region sometimes you see some fast ones coming out. The lengths of these strips are also is identical to their velocity, and you see here sometimes you create some fast neutrals. These are the charge exchange vectors I have mentioned before. Now we have everything. Now we can analyze, for example, coupling the system to our erosion codes, the erosion and the characteristics of the system. And this system is insofar nice. If you remember, due to these very constant potential conditions, the radial drop is also quite small. That means all the ions hitting the wall have very low energies. It means within this panel, the mean energy of the ions here for the hand are practically 20 eV maximum, maybe 50 here at the end. And here, for comparison, these are runs for standard Holzraster, where they always have the problem that the energy is increasing and you start erosion. Also here you see the fluxes. If you put this together, you see the second nice property of the system. You have practically zero erosion. And this is something which is very important. That means you are easily able to obtain more than 30,000 hours of operation. And you see here, for comparisons, the typical sputter erosion rates for Holzraster, which are order of 1 millimeter per 1,000 hours. Hemp is invisible. Hemp is this red line here on the bottom, which is at zero. It has very, very low erosion. And this is just the reason of this extraordinarily nice potential profile, because you have no generation of energies which allows you to activate this button. Now just an appetizer for three-dimensional results. I told you before that in a hierarchical way we try to cross-validate our things with the higher hierarchy. Here we did a very nice collaboration with Princeton. They have an extremely good diagnosed system, the so-called cylindrical Holzraster. And we use this to compare some of our three-dimensional photons, including self-consistent turbulence. And I just want to show you as an appetizer a dynamic result of such a system. And what is important, if you just look at the C equal 2 and C equal 5 millimeter case, you see rotating elements, slowly rotating element. In the electron density, the other things are potential and neutral density. And what is important, this is an instability which is also seen experimentally, and there's a lot of effort trying to understand this kind of phenomenon. And due to the simulations, we think we have understood the reason. It's interacting with the neutrals. This defines mostly the friction which is setting up this rotation, and also the rotation frequency, rotation velocity is in agreement with experiment, because both are in the order of 2 kilometers per second. Here you see such a rotating spoke in an experimental view as seen in the experiment in Princeton. Now, so far so good, but the world unfortunately is never so wonderful as it looks like. Even applying this particle in cell, we clearly have still a problem that we want to address, also the Bloom problem in a kinetic way. And the problem which is, so to say, appearing is this difference of your device scale. We have this device scale, so 20 microns in the system, a millimeter outside, and peak is usually only correct as long as you have equidistant grids. And the second problem ion distributions were not realistic because we were limited in grid size. And to overcome this grid size limit, I show you what we do now. We developed a better way doing particle in cell codes. Up to now, practically everybody who's using anisotropic non-equidistant particle in cell is doing something wrong, because the creation of these non-equidistant particle in cell codes, which have varying cell sizes, suffer from the problem that you then artificially introduce cell forces. That's non-physical, that's completely nonsense. It means never trust these results. And I'll show you here an example. This is the result, just moving one electron through a one-dimensional system. And here you have a jump in the grid size where it passes. And you see without correction, you just get your cell force, and it's just wrong. Now to overcome the system, or the system problem, you can just introduce very simple different interpolation of your electric field in these kind of jumps. The trick is you just interpolate back to a symmetric situation, and by this you can make very nicely the cell code disappear. Now with this kind of setup, we have now a tool attempt to run non-equidistant particle in cell code for such system, attacking also the problem of the blue. And I show you now one example where we used this larger domain, where we varied already the position of the neutralizer, marked in black here, and you see moving the neutralizer source, we can very nicely optimize also our distribution of the ions, which are following mostly here these ion density lines. The original neutralizer has this bending to the left. If you are able to move this further in, you see how your emission and your potential structure is following this, and you get a much nicer beam cover. Also, clearly, already with the original system, due to this expansion of the domain, we were now much closer to the experimental measured ion angular distribution, and we match now also this in the simulation. The last part of the talk is an example how you interact also with respect to other things using such simulation tools with experiment. A problem for the people is they have to test somehow their thrusters. And for thruster testing, they use terrestrial tests. They use a large vessel, 10 meters, and then you have your small thruster, and then you measure your distributions, your thrust, and whatever you want. However, unfortunately, whenever you have kind of stream of ions going out, they will intersect with your walls, and you will have sputter fluxes coming back. And I mean, you have here test times of thousands of hours. That means even if the flux is small, you can have a deterioration of your thrust and of your whole system from these back fluxes from the walls. And we were suggesting, first we were analyzing the back fluxes because they were interested what they get. And we were analyzing for them a system in Italy where the tests are done. And then we suggested a simple idea. Why not introducing here baffles? You see here, this is the typical distribution of such a sputtered particle cloud here from the wall. You typically should say cosine distribution. That's a little bit more complex than that, but take it as the first rule of thumb. Then you introduce your baffles like this. You just move the emission direction away from your thruster, and they move inside your vessel, but they will not come back to the entrance of your thruster. That means they installed a complete set of these baffles, and were able to reduce by a factor of 10 their backflows. Very simple idea, and that's something you can bring over as a theoretician back to experiment, and they are happy if they get support to solve that problem. Now, I'm over. No, I still have time? Okay, I'm too fast. Okay, then I do a little bit more in the summary. I hope I convinced you that something like modeling is a good tool for supporting not only basic physics understanding, but gives us also a chance really helping industry to advance their products. That means we have a chance where physics motivated industry-oriented work, so to say, is possible using modern tools in combination, both, and that's very important, both of numerics, physics, and analytics. We have seen to be successful, we need a combination of good codes, good physics, and analytics in terms of using, for example, the similarity law and having benchmarks to be sure that the codes are doing something right. Here, in addition, we want to have perfect combination with the experimentalists. We need excellent diagnostics, only then we know if the codes are okay or not. In this case, we were very lucky that we got in contact with our colleagues from Princeton, who have extraordinary well-equipped experimental facilities, looking also more from our point of view into the physics and being less optimized like the industrial people. Therefore, this was very helpful. Overall, fortunately, the funding agency is ready to continue with this because they see this also as a good chance for them getting a little bit more academic profile. And I would say we have everything at hand. We have the right tools, we have the right partners, and we are ready for liftoff. Thank you.
Thank you very much. So,
Ralf, have you written out something on the non-equidistant grid, like a paper or something?
Yeah, that's published.
Yeah,
That's published.
I'll get the reference from you.
Thank you very much, Ralf. I have actually two questions. First, you listed the different processes you take into account with Xenon. Is there also stepwise execution of reports and you?
Yeah, I just cut it here in the list, but we include also the second charge state, and if needed, also the third charge state. But that's in this case not needed. We have a little bit secondary charge, but practically nothing is on the third charge.
Yeah, but also for the excitation, so there might be not direct excitation.
These are effective rates, they are included. We have collisional radiated models for that. That's like in fusion. No problem.
When you move into a neutralizer close to the axis, then you enhancing the sputtering.
It will not be possible to build. The trick is you can modify this. That's so to say the simple physics idea. You just increase your energy, increase the radial transport over the magnetic field lines, simulating this position with the original neutralizer. You have a free parameter. That's the energy of your electron. And then it means in fact, I mean, this is the way to go. You can't put it here. I mean, it's just disappearing, hopefully.
Yes, well, another question might be interesting for the colleagues working in high-term sputtering like Witt and Achim. So they also observe this spokes, this running spokes in the sputtering. Do you think there's any chance to explain or also to model with your ideas here the situation in the magnetrons?
In principle, magnetrons are also accessible to particle itself, but we have done no work on this region. I mean, it's always a question what are the typical scales. And I would say if you start from scratch, you always need 2 years to understand the system. I mean, don't believe these codes are, I mean, everybody can have our codes, but you will produce only rubbish because you don't know what you are doing. I mean, therefore, I mean, it's not black box physics. You see, you have to get into the system, you have to understand the details, you have to find the hierarchy of the text, and then you decide what you do. Therefore, 2 years, yeah.
and then
Okay, what ask you about the charge usage? You can stay on that.
That's Xenon here. This
What
thing.
about the usage of a
The reason for Xenon is very simple, high mass. And then it's, so to say, non-reactive. What do you want? You want to have a non-reactive gas with high masses. And it should be easily available because everything must be simple. If you have other suggestions with fit this boundary condition, no problem. People would be happy.
You mentioned better color simulation of secondary recognition. Is it important about the beam acceleration? Because I don't get the
yeah, here this is a particular thing because we have this dielectrics put in by purpose because it has very high secondary electron emission. And it in total it optimizes the efficiency of your ionization because it transfers hot electrons into a cold region there and it produces some additional kind of lens effect from the charging. It means, in fact, the dielectrics is important both from the secondary electron emission point of view and from the shaping of the system. But these are real details.
What about a magnetic field? Do you one cusp or 2 cusps on
this case, up to now, people have reduced it just to 2 magnets that with the 2 customers. I showed you at the beginning, a sketch the 3. You could add more, but you don't benefit from it.
Okay, so 2 is ideal.
That was at least the experimental finding.
And your code does not take into consideration, does not study.
We haven't tested that. That was nothing they were interested in.
Okay.
I think that's also relatively simple to understand that you don't gain much if you have more.
I believe that's the spots people were talking about, or rotating kind of waves. This feature is seen on almost all linear universal waves.
As well, yeah.
And
It reminded me also of this.
people are debiting it from the big waves.
Yeah, here it's really this coupling for neutrals.
Neutrals definitely play a role.
That's like I said. The interesting thing is due to this high density block, you excite high fluctuation levels. It's a lot of turbulence suddenly existing. That was a prediction by the code. Unfortunately, the experimentalists saw it then also.
Yeah, I think it was enough questions, so thank the speaker again.